Hi everybody, this is electrochemistry and the first part is potentiometry. We have discussed in class and we also have known about the electric potential as well as cell potential. So the first topic that we are going to discuss is potentiometry. So what is potentiometry? So this is basically what is potentiometry, and you can see that potentiometry involves two sets of electrodes. You can see here reference electrodes inside the glass electrodes, and this is the thin glass membrane electrode as working electrode. Okay. So the principle, because we need to discuss first, is the principle. So the principle of potentiometry is the analysis are based on measuring the potential, okay, of electrochemical without the need of current. The principle the principle of potentiometry is the measuring of potential due to the chemical reaction, and the chemical reaction is spontaneous without the needs of drawing a pushable current. Means that you do not need so much current in order to make sure the electrochemical reaction to happen. From the electrochemical reaction happens, it provides potential difference. So that's how the principle of potentiometry. So the techniques can provide a rapid and convenient means of determination of anions and cations, such as pH. So in potentiometry, it is requiring the use of reference electrodes. Okay. Reference electrode, and in order for you to answer final exam you need to know what is the function of reference electrode. Okay. The function as well as the characteristic of the reference electrode. So reference electrode, it has a known electrode potential, remain constant and independent of the composition of analyte, means that it will not respond to any analyte concentration. It's supposed to be constant. Whereas indicating electrode or working electrode, the potential is responsive to the concentration changes of the analytes of interest. So in short, for potentiometry, the cell potential is equivalent to the cell of the indicating electrode or the working electrode minus the cell potential, the electrode potential of the reference electrode, as well as the liquid junction potential. So this is one example of a standard reference electrode using hydrogen electrode. So this hydrogen electrode is considered having electrode potential with the value of 0. So in this structure of hydrogen electrode, we can see that this is hydrogen. Because it is in the form of gas, the unit or the concentration is based on partial pressure, which is 1 atm. And this is how the structure of whole hydrogen electrode, and the inert electrode used here is platinum foil. Okay. So this is the reduction, okay, involves reaction involved for hydrogen electrode. So hydrogen gas reduced to 2H plus, by right it's 2H plus, okay, plus 2 electron producing hydrogen gas. It's supposed to be 2H plus, okay. So this is the, if you remember, the what we call as I forgot. Right. Okay, so this is another example of reference electrode. It is called calomel electrode, and this is based on mercury. Okay, it's not being used right now because of the usage of mercury. It's very toxic, so the best option is hydrogen electrode. Okay, this is another reference electrode, AgCl, and this is the standard reduction of AgCl. You can see from Ag plus here, receive electron forming Ag solids in elemental form, chloride, and this is the whole reaction. Okay, so this is these are example of reference electrode in potentiometry. And these are the suitable potential for all the reference electrode. So what is liquid junction potential? So liquid junction potential develops across the boundary between two electrolytes with different concentration. So we can see that 1 molar HCl and 0.01 molar HCl. So due to different concentration, the hydrogen ions and chloride ion tend to diffuse across the boundary. Of course, from more concentrated to less concentrated. So these provide what we call as potential of liquid junction. So we need to minimize this, okay? We need to minimize the liquid junction potential. So by placing a salt bridge between the two solutions. So if you observe the hydrolytic cell or potentiometric cell, okay, it requires what we call as salt bridge in order to remove or in order to minimize the liquid junction potential. So examples of salt bridge is saturated solution of potassium. Okay, means that a very high concentration of potassium. Effective if the mobilities are okay. So this will reduce the migration of ions from the high concentration to low concentration. And therefore, it can reduce the liquid junction potential. So those are reference electrodes and liquid junction potential. So now is the indicator electrodes. So you can see that we have a series of indicator electrodes. It can be metallic, membrane, ion sensitive, or known as ISE, or gas sensing electrodes. So this is an example of metallic electrodes where you use metal as the indicating or working electrode. And this is the nurse equation, okay, involving the reduction of the cations, okay, that is involved in the main reaction. And this is the activities. Okay, A is the activities representing the concentration of the ions or cations. Of course, it is not very selective and respond only to their own cations. For example, if you want to analyze copper, okay, copper ions, so we use copper metal as the electrodes. Some metals are easily oxidized, okay, so it's not really useful for indicator electrode. The second type of electrode, okay, we can use, for example, AgCl, but also the activity sparingly soluble precipitates. Okay. In this case, we are using silver electrodes. Okay, that correlates to the activity of chlorides in a solution saturated with silver chlorides. So you can see that we are using AgCl, okay, as the indicator electrodes. Ag as the electrode, and it is responsive to activities of anions that form sparingly, in this case, sparingly soluble precipitates or stable complexes with such cations. So this is the process of using electrode of second kind. We can also use inert metallic electrodes. In this case, platinum electrode. Membrane electrodes. This is another example of working or indicator electrodes. It is called membrane electrodes, and this is quite common, especially in the lab. We are using this for pH meter. Okay, so you can see that we have reference electrode, AgCl, and the glass membrane is itself an indicator electrode or working electrode. And you can see that we have KCl, okay, as the minimization of liquid junction. Okay. So this is the what we call as the whole reduction oxidation process. Okay, and this is what is happening in the anode, and this is happening at the cathode, and this is the salt bridge. Okay. So these are more complicated, which there are certain functional groups attached to the glass electrodes, okay? Not just pH. We can actually measure anions, cations. It depends on what are the functional groups involved on top of the membrane electrodes or glass pH electrode, glass electrode. So this is an example. You can see that glass membrane only allow, in this case, we are talking about a pH electrode. This is how it works, okay? The H plus ions incorporated in its inner and outer layer, inner and outer layer. This is outer layer, and the inside of the membrane electrode. The inside is filled with fixed concentration of H plus, okay? Whereas the outside should have the one that we wish to measure, means that it is unknown. So the inside of the glass electrode is fixed concentration, whereas at outside is the one that we need to measure, means that it is unknown. Okay, so the difference of the concentration of H plus inside and outside the glass will generate a potential difference. Okay, so that's what we are focusing on. Okay, and this is translated into pH reading. So when we have a bigger difference of concentration of H plus, it means that more potential is generated, and that in that case that we can translate it into pH 1, 2, 3, and so on. So this is very important, that in order for the pH meter to work, it has to be in wet condition. It cannot be in dry condition. Okay, so this is a whole redox reaction involved in the glass pH electrode. So 4 potentials that develop in the cell when pH is being determined with glass electrode. One is the liquid junction. So this is the whole redox reaction that is happening for the glass pH electrodes, and this is the supposed to be the liquid junction. Sorry, the working electrodes or indicating electrodes, and we have the reference electrodes. The net potential, of course, the salt bridge, EJ, I'm sorry. And the force is the boundary potential, which varies with the pH of the analyte solution. Okay, it separates the calomel electrons. It seems that the system has two reference electrodes because it has internal reference electrodes, and this is the working electrode. The potential, okay, that is generated is due to the difference of charges, means that the difference of concentration of hydrogen ion, because this is the one that we measure for pH between two surfaces of membrane. Okay, there are reference electrode inside the same inside the membrane working electrode. Since the amount of charges inside the membrane almost constant, because we put in fixed concentration of H plus, and the boundary potential is then measure of the hydrogen ion activity outside. Means that in the beaker where you put the solution of the solution that you wish to measure the pH. So this is at outside solution. Okay, so this is something extra. So we don't need to do this. So basically, we have in basic solution, glass electrode also can respond to the concentration of both hydrogen ions, okay, and alkali metal ions because of the same charge. Because you know H plus relatively to the group 1, for example, potassium plus, sodium plus, so those are alkali metal ions, and it is called alkaline error because of this responsive towards apart from hydrogen ion, it is responsive to alkali metal ions. So the alkaline metal ion, the alkaline error can be satisfactorily explained by assuming an exchange equilibrium between the hydrogen ions on the surface of glass electrodes and the cations in the solution. Okay, so if there is other cations, for example, alkaline metal ions, then there is a possibility of alkaline error. So there are also glass electrode also can be used to measure other cations, okay, apart from hydrogen, okay. But then, as I mentioned in one slide, that you have to modify the surface of the glass electrode. You have to modify the surface of the glass electrode. Okay. Modify the surface of the glass electrode with certain functional material. For example, we have aluminum oxide, boron oxide. So this can be done in order to detect cations apart from hydrogen. So glass electrode also can be used as selective electrodes for cations other than H+. So this is another example of indicator electrodes. So we can actually construct this electrode by ourselves. You can see that it's just plastic tubing or glass tubing if we have. And then we can fill up the plastic tubing with saturated aqueous solution for the salt bridge. And we can have membrane that we functionalize or do ourselves in order the membrane can do ion exchange. So in this case, that we can use this homemade electrode as the indicating electrode. So this is another example that you can use to modify the surface of the electrode just now. Okay, if you can see that it is membrane. Okay, so the membrane can be incorporated with what we call as ionophore. Okay, so this is example of ionophore. Okay, it is called crown 6, and this is very selective for potassium or K+. Okay, so we can construct the electrode ourselves. Okay, and then use it for detection of cations. So there are other types of working electrodes. So I think the class, the topics that we are going to discuss is up to the glass electrode only. This is another example of working electrode where you can incorporate gas permeable membrane on the surface of the electrode, so you can detect some gases. Okay, for example, we can have polymer on top of the gas membrane, so that we can sense gas, for example. So that's it for potentiometry. And these are the applications of potentiometry by using ion selective electrodes or working electrodes.